Hey everybody, today we're going to solve what is this problem called? Evaluate division problem on LeetCode. Okay, so let's just run through the problem description really quick. We're given these equations in the format of a divided b is k. A and b are variables represented as strings. K is a real number, floating point. Given some queries, return the answers. Doesn't exist, return -1. So let's expand this out and see what this looks like. So a over b 2.0, these are the equations that we're given. A over b 2.0, b over c 3.0. And then we're asked, what's a over c, what is b over a over e, a over a, x over x. And here's the answers. So a divided by c, 6, b divided by a, 0.5, a over e, returns -1. There is no e in the input, so that's obviously not valid. A divided by a, just 1, x over x, -1, there's no x in this input. Okay, so this is not that simple of a problem. And it takes a little bit of thinking, but basically this is a graph / depth first search problem, and that's not evident at all when you first look at it. So when I first saw this problem, I started poking at it and coming up with some different approaches. Nothing was really working. So for me, when I'm working a problem and I'm working different approaches and having difficulty finding something that's going to work, graphs usually start popping up. Okay, and you say, if you look at this and you go, well, what could this be represented as if it's a graph? Well, if we represent this as a graph, we can take our input here. So our input a, b, and c. Okay, we're given a, b, and c here in our input equations. And we can say, okay, this is basically a relationship. And a and b are connected in this graph. A and b are connected. And it's a weighted graph. It's a weighted directed graph where the edge from a to b is 2.0. And then the edge from b to a is 1 over 2.0. And then over here, b is connected to c. B and c are connected in this graph. And the edge from b to c has weight 3.0. And then the edge from c to b has weight 1 over 3.0. Okay? And basically all we have to do to solve this problem is run depth first search from the start that we're given till the end, and keep track of the product of the weights of the graph as we traverse the graph. So that's all we really need to do. Like I said, that's not evident at all when you first see this problem. It's pretty difficult and it's kind of hidden, right? Unless you're extremely experienced with these kind of things, the idea that this is a graph problem isn't going to jump out at you really quickly. But once you start trying to approach this problem, you'll start to see, well, it's pretty difficult to come up with anything that works. Okay, maybe graphs, maybe some sort of a search algorithm. And then when you start thinking graphs or search, and you see, okay, what am I given here in these equations? Well, it's a relationship between two different things. And these two things are connected in my graph, as well as these two things are connected. And here's the weight on the edge, okay, the weight. So from a to b, again, 2.0, and then the reverse for b to a is 1 over 2.0 for the weight. B to c, 3.0, and then going back, c to b is 1 over 3.0. So that's how this graph is constructed and how it looks, okay? It's a decent amount of code to write all this up, so I'm not going to go through typing all this. I think that's just a waste of time. So we'll just kind of talk through what each bit of this, each bit of the code does here. So take a look at this class that we've got here called node. Okay, this is going to be a node in our graph. It's got 3 members. It's got its string, which basically represents its value. A state represented by integer. For state, we're using 0 is unvisited, 1 is visiting, 2 is visited. And then a map, which is nodes to doubles for its neighbors. Okay, so it's going to have a node as a key in this map, meaning it's connected. It has an edge going to that node, and the double is the weight of that node. and then we just construct it here pretty simply. And then down here we have our class graph. It's going to keep a map of strings to nodes. Okay, so we can keep track of what nodes are in this graph. Construct it just like this. And then here's sort of the key part of the problem here. We're going to build this graph. Okay, we'll build it from these equations that we're given, which are these right over here. A over B is 2.0, B over C is 3.0, and so on. So we're building it from those equations that we're given. And then the values are the answer. Okay, so where do they show the values over here? Yeah, so the equations that they'll give us are in the form A over B, and then the equivalent value will be the answer, which is 2.0 right here. So that's how they give us this data. So we're going to build the graph from that. So what are we doing here? We're going to loop through those equations, pull the equation out, and the value, which is the answer. And here's the first and second variable. We will put them into the map if they're not there. And then basically we just add the connection. We add the edges. So we get the first value, we get that node, we add a neighbor to it, which is the node of the second value, and the weight is just the value. And then we add the reverse edge. So we get the second value, and we add a neighbor to it, which has weight 1 over value. And that's all you have to do to construct the graph. Okay, so you construct the graph just like that. And then down here I added something to the graph class reset states. Basically we need to reset all our states to being unvisited after each query that we answer, or else we won't find answers for following equations. So here is the method that LeetCode actually sets you up. Calc equation gives you the equations, the values, and the queries. So we build our graph from those equations and queries, set up an answer which holds the answers for each query that we're given, and then we just loop through the queries. Okay, we pull the start and then the end nodes from our graph, and then we just run DFS from the start end, and we pass in this initial product of 1.0, and that's all there is to it. And then the DFS is obviously what's doing the magic here. In our DFS, if either of our nodes are null, we don't have an answer, we just return -1. If the start's value is the end value, meaning we're at the node that we're searching for, we'll just return the product that we have. Mark the start as visiting. We'll loop through each of its neighbors. If its neighbor is unvisited, we will compute an answer from that neighbor using the neighbor as the start, the same end, and then the product that we've been passing around times the weight. Okay, so we're multiplying by the weight to get to that neighbor, the weight of crossing that edge. If we found an answer, if it's not -1, we'll return that answer. Down here we mark as visited, and then we return -1 if we don't have an answer. So let's see if that works. Alright, cool, so it does work. So again, this is not a problem that looks like a graph problem straight away, but once you start thinking in terms of graphs, it actually makes it pretty simple. I'll just kind of scan up here. So if you want to pause the video and just have a look at the node and graph classes that I defined up here, because they once you define these things as nodes contained in a graph, that makes the depth first search very simple. So again, here's the node class, the graph class, this is the method that LeetCode originally gives you. Basically all we do is construct our graph and then run depth first search. And here's the depth first search, which does all the work.